All right, so here's an ICR one, and taking a look at the problem here, trying to find a straight edge. This one, I think this is actually an acceleration problem, but we could do the first part of it as an ICR, right? No, it just asks for the angular velocity, right? So the angular velocity of this, we draw the thing out. And looking at what the velocities they gave us right here, well, first off, we can get this guy's velocity. This guy's going at 6 radians per second. So it's going to have a velocity of B is going to be right there. All right, and so we know the velocity of B is also going to be right there. And I didn't mean to do that. Where'd you go? Right there. Come on. Purple. Purple. Purple, you bastard. We know that the velocity here has to be in this direction. So the ICR on this one's actually pretty easy, right? Because all you have to do is draw lines. That's the important thing for the ICR, is to draw lines perpendicular to the velocities, right? Don't, because it's really easy sometimes to to just draw a line in line with the velocity and like think that the ICR is right there. It is not. So the ICR is going to be right here, because this and looking at this, we could see right away that the angular velocity is kind of hard to draw it that way. Let's see. I'll try to draw it. The angular velocity of BCD D is going to be in that direction, right? And then you could find with the velocity, I guess we'll draw green again. It's going to be like right here. That's going to be the velocity of C. I think I got that right? Yeah, sure. So all we had to do was to say that VB is going to be equal to omega AB times the L of AB, or 6 times our 200. We can keep it in millimeters, right? So 1200 millimeters per second. And then we could figure out what, we do a little geometry there. Or actually, we don't need to do much geometry, right? So, because we already just know that the R of B with respect to the ICR is just going to be this 150. So we could find that the omega BCD is going to be equal to VB over RB with respect to ICR. Or just the 1200 divided by 150. And our Hewlett-Packard 35S says that's going to be 8. And so that's actually, I think, the answer that they were looking for. But I would probably ask for something a little bit more involved, where I would ask for maybe the velocity of D, right? So in doing that, you could actually ask the velocity of C. If you wanted the velocity of C, you're just going to get omega BCD times R C ICR. And we can see that the RC with ICR is just going to be, double check, yeah, 300. So 300, well, do it in the right order. What you doing, bastard? What'd you go to that for? What'd you do that for? Erase. 8.00 and 300, or 24. And then a little bit more challenging is if you ask for the velocity at D. Now we got to get this distance right there, and that requires us to do a little bit, not too much, because that's just going to be R D with respect to ICR. We would probably take this distance. Well, no, I'll take that back. This distance, right? That's going to be that distance. So the square root of 100 squared plus 500 squared. Or 509.9. So VD is going to be omega BCD times RD with respect to ICR, or 8 times our 509.9 to get 4,079 millimeters per second. And, asking for an ICR that's too much more difficult than that, it's just kind of cruel. And if you want to try to ask, especially if like the geometries get really weird, those could be really time consuming, especially if you're frazzled during an exam. If you get a kind of weird one that goes up like this right here, and we get some kind of weird, triangle that's up into space, and there's no right triangles as part of it, and now I got to go law cosines and that kind of thing. That can be really irritating. Let's see other requests that we had. Let me see what we asked for. I'll do a projectile motion in a bit. Let's go for Jonathan wanted an impulse and momentum. I want to double check it's still being recorded. Yes, we are being recorded. Okay, good. So we could go back away. Go away. Boom. So let's see. I don't know if I have one off the top of my head, but we can go back and let's see. I will keep all this for now. Then you don't need to be that loud. We can all hear you. Let's see. Impulse and momentum. Rigid body, impulse and momentum, I'm assuming. Yeah, that's what he said. I could just start wandering around the book, but let me use the table of contents instead. Momentum methods. I think this is still, that's still two-dimensional rigid bodies. D'Alembert. I love that guy's name. D'Alembert. Momentum principles right here. So force, linear momentum, moment of angular momentum principles right there. Energy and momentum of planar and rigid bodies. So it's probably going to be this one in chapter 8, I'm going to guess. So like page 415. Making drinking noises in front of you. That's rude. Don't be rude. 415. You could just go on a little bit further. So like this kind of problem right here. Like I think this is a pretty good one. But it's not that much different from other ones that I've done as examples right here. Okay, well, you got a coefficient of restitution right here. Ooh, and now you want to know the total kinetic energy of the sphere and ball after it has been the impact here. Those are all good. Those are all good things to know. But I don't want to spend too much time on any particular problem. But I kind of like that one a little bit. I don't see any that I'm in love with. Boom. This one, this is an interesting one down here too. Where you get this bar hitting this other bar. It's better when I do these when I have the solutions. So I'm going to see if I have, I don't even know if I have the solution manuals to these. So let's see, the problem that I just looked at, this is like chapter 8 right here. So I do have the solution manual here. So chapter 8. Oh no, this might be the ones where they combine statics. Like so this is like a newer version right here. I'm going to guess chapter 17. And let me paste this guy in to one here. So it'd be good to it's good to just see if I get the right answer or not. All right, stop it. Leave me alone. And he says, can we work through the question from the review packet on page 5? Okay, I'll get to that one after I finish this one up. Okay, let me just double check. This is, let's see, what did I say? That was problem 864. So there'll probably be, if it's going to be if this is the right chapter here. Oh, come on, get back over there. Move. All right. Down to 64, thereabouts. 64, and that's rigid bodies. Yeah, so it's probably going to be chapter 19. Right here in chapter 19. That actually seems kind of late. Oh, come on. I want instant gratification. Yeah, that looks about right. Looking. Yeah, okay. Yeah, they got it. Yeah, about that. That's cool. All right, so in this problem, it's a little more challenging than was done in the homework problems in terms of rigid body impact, because it doesn't have a pin joint. So you have to you're going to end up using two equations or two methods, and you might actually need 3 equations, and I believe you do. Okay, so what we have here is we have this 1 kilogram sphere, and it's moving at 10 meters per second, and it's going to strike this 4 kilogram stationary bar that's 2 meters long. And with this first one, we want to know if the sphere adheres to the bar, what is the bar's angular velocity after the impact? So what we have going on, what we're going to use is the principle of angular momentum. So we have before impact and then after. So we have this collision, and that's going to equal to the parts when they get stuck together. So here we go, and they're going to have the mass of A times the velocity of A1, and so that's going for it. And then after we're going to have this kaboom, equal and opposite impulses. Did I mention I have poison ivy? I got it from planting wildflowers. Now, it strikes me, now that I think about it, as a little weird that you would plant wildflowers, right? Shouldn't they be wild? Mass times of A times velocity of A2. We're also going to have, and we can, let's assume counterclockwise. It makes sense that it would be, so it's kind of obvious. We could have the moment of inertia of the bar about its center of gravity times its angular velocity. We could just call it angular velocity 2. But we're also going to have, and maybe I want to like leave myself some room here, because we're also going to have the motion of the center right here. So we're going to go I omega 2, and then we're going to have the mass of, I guess we could just call it B, because and the velocity of B2, and by that we mean from the center of mass right here. So we take our impulse and momentum, and we take it about the center of mass to start with, right? So we go the angular momentum before, and let's just go center of mass, maybe 1 plus the sum of the moments dt, right? And that is a vector. So I almost gave it a hat on accident. It's going to be equal to the sum of the angular momentums about the center of mass afterwards. And got to remember these are vectors. So we take a look, and on here in the beginning, we have mass of A, velocity of A1, and we're going to pretend like it hits right there on the tip, right? So that's going to be, we'll just say LB over 2. And it's going to be positive because that is counterclockwise, right? If you were to draw, we take that as if it's going about the center right there. And then we get to the middle diagram, and there's nothing there because these are opposite from each other, equal and opposite. Then we get over to the left-hand side, and we're going to have the mass of A times the velocity of A2, once again, LB over 2, right? But then we're also going to have the mass moment of inertia right there. So we could find that mass moment of inertia, by the way. We could do that over onto the side. We could have done it right away. 1/12 m LB squared. And the mass, what I say, it was 4. And the bar was 2 squared. Should be able to do that in my head, but I can't. 16 divided by 12. That's like 4.667 kilogram meter squared. And so as we stick stuff in here, we let's see how much he weighed. How much says it was 1 kilogram, and he's going 10, and he's 2 over 2. It's going to be equal to the mass is 4. Nope, it's still 2. Still 1. VA2 2 over 2 plus 4.667 and times omega 2, right? So I like to, but that's just going to equal to 10. It's going to be equal to VA2 plus the 4.667 omega 2, and that's going to be the first equation that we get. Now we need another equation. Where are we coming up? I have another thing. Oh, you think it's 1.333? I bet you're right. Right? Because it shouldn't it be 16 divided by 12? Yeah, that sounds a lot better. I don't know. Yeah, thank you. The calculator's sticky or something. I don't know. Thank you. 1.333. Oh, and I don't think I mentioned that this problem is not in the solution manual, so we'll have to go about never really knowing. We could probably just search it on Chegg and find it on Chegg. Let's see. Okay, and then so we have one equation, we have two unknowns, and we need to relate VA and omega 2 together. So, but VA2. but we know that they're going to stick. What we could also do, if we were going to do this properly, just to make sure that you know how to do it properly, the other equation we would need is the coefficient of restitution, right? Where we would say E is going to be equal to the relative velocity after divided by negative relative velocity before. Or you could say it the other way, negative velocity after divided by the relative velocity before. And we want to be careful because I used up here, I used VB to represent the center of the mass of this thing, which isn't necessarily going to be true, right? It's well, no, I'm sorry. It's not. It will be true. But what I would rather do is also define a point on the bar as something. So I'm just going to pick C, right? And so those are the points that we have to use for a coefficient of restitution. It's very important. So we could say that VC2 minus VA2, because those are the things impacting. VA1 minus VC1. Now, it just so happens as part of this that VC1 is going to be 0. And we know that what happens, okay, if the sphere adheres, that means that E is going to be equal to 0. In this case right here, this first part. That means that we could just look at the top of it and we could just say that VC2 is equal to VA2, and we didn't need the coefficient of restitution to know that. We would know that they would stick to each other and they would stick, okay? So, but that right there is like the formal thing that helps us if we have something that's a little more complicated than that first problem. And so now what we could do is we could say that we know in terms of the bar, right, that we're spinning right here, that this point right here is VA2 is going to be equal to VC2 right here. So here's your VA2. But we also have a VB2. Right, so that's like the confusing thing here. We might, if we were just not thinking, if we're just going on cruise control, we might say, well, say, you know, this is dumb guy, right here. This is confused guy. He thinks, well, isn't just VA2 equal to omega 2 times L over 2? Is that true? Anybody? Just say no. No, it's not. Because this is a rigid body and it's not a constrained problem. So it is translating. And it will translate like VB2, or it'll translate by any way that you want it to. So it has a kinematics relationship. Something like that, spelled like that. That's going to be equal to some reference plus the angular velocity thing. That's the thing that's going to tie these two together. These two are related by more than just something simpler like this. So what we'd say is like, well, we'll pick one as being the reference. Let's pick VB2. Let's pretend that we know that. So we put them in both places. So there's VB2. And here's VB2 right here. So that means we're going to pin it at VB2. And it's going to rotate, we presume, this amount, omega 2. So now we're going to have a V A with respect to B. Right? And that that is equal to omega 2 LB over 2. So we know that VA2 is equal to VB2 plus omega 2 LB over 2. And that is our second equation. But unfortunately, we've now introduced an extra variable. So what do we do about that? We have two equations and two unknowns. What do we do? Anyone? Take a guess. Well, we have two equations and three unknowns. VA2, omega 2, and VB2. Yeah, almost everything's moving in the X direction. I didn't give myself enough room. Oh, you know what I could do? Maybe? Is this going to be a cheat? Is this going to work? I'm a cheater. See, I should be doing all this in OneNote. So a couple of my colleagues have been using OneNote instead of... but I like the fact that I get a little bit more on the page when I do this with here. Well, I have another principle that I must have forgotten until now. Linear momentum. Remember, this was angular momentum. This is angmom. We got linmom. So we can write for the same diagram right up here. It's just we could say the sum of the linear momentum. Just call this L1 plus the I could say the summation or the integral of f dt is going to be equal to the sum of the linear momentums after the time. So we have mass of A times velocity of A1 plus 0 equal and opposite right here. It's going to be equal to MA VA2 plus MB VB2. We have a third equation. Yay! So now we have three equations and three unknowns. We can solve it. Do I need to solve it to take the time to actually throw numbers into this, or do you think you could solve it now? We could use our time more efficiently, I think, maybe to go to another type of problem. The big thing that I want, big knowledge thing. Rigid bodies. Trans and rot. Keep in mind, both of those things are taking place, translation and rotation. So we did the rot up here. Now we could do the trans down here. And we could tie them together with kinematics and some principle that we know of. So we could actually, so when we get to, and the reason why we even wrote this one down is because we could change the problem, right? And have the E, have the coefficient of restitution. Now we're going to, then we'd be able to have there would be another equation that we would need to know that would be for VC, right? We were able to, and I guess we still kind of have, this is actually probably the third equation. This is probably the fourth equation, right? because VC was one of the unknowns that we had right in there. But I didn't number them that way. So are we good? Does that make sense to everybody? Anybody? Sydney says yes. Okay, was at least one person. If you didn't understand it, if there's you got some question about it, or if you thought about, well, how was I supposed to know that? How was I supposed to think that way? It's totally a fair question. It's not necessarily obvious. When you see the answer, it's obvious. But it's like the mindset, the kind of the thought process of like, if I get stuck somewhere, not to just throw our hands up in the air, but to just start thinking through, go down the list. What do I know? What do I know? What do I know? What are the keys? What are the things that could be stumbling blocks? And so that's why I'm making this thing right here. That's why I'm jumping on this, putting stars next to it. That's how you would know to do that on the exam. You would go and you would get stuck. You said, damn, I got too many unknowns. What else do I know? What else do I know? Oh yeah, it's a rigid body. It is translation and rotation. So what does that mean? Oh yeah, I could do linear velocity, linear momentum as well. All right, so let's see. I'll beat that one into the ground. Okay, we had someone asking for, what did we say? Can we do the question from review packet on page 5? We'll do some angular acceleration stuff coming up too. So which one's page 5? Let's see, you could do the question on the review back page 5. I don't have them numbered correctly on mine. That one, working energy. Yeah, I wrote this problem. You know, younger than me, wasn't that long ago. I guess it was 6 years ago. Time has flown. And let's see, how many pages? I did multiple pages in the answer. Okay. I thought of this as the kitchen sink one. These kitchen sink ones take a lot of time. And they're not very nice. But listen, it's working energy. And they have a 60-pound wheel with a radius of 2 feet. And it rolls on its hubs, which have a radius of 6 inches. Down the inclined rails without slipping under the action of an applied cable. Right, so this cable is being pulled out. It's got and the tension. Somebody's doing a good job, and they're keeping that of 16 pounds. It's pulling against a spring that's 12 pounds per foot. I put them in pounds per foot instead of pounds per inch just to be a nice guy. The cable unwraps from the wheel as it rolls. Okay, so this is, if you could picture what that looks like, right? This actually looks like a drum, right, where it's got like of cable. You could think of it as and it's got like these little kind of things sticking out the side of them, and it's really on this that it's going down, right? I didn't do a good job of drawing that other side right there, but it's on these little rails, and somehow somebody's pulling this cable and keeping it with a constant tension as the thing's rolling. And I also give you that the radius of the gyration of the wheel and its hubs is 8 inches. The wheel is released from rest when the spring is unstretched. Okay, so at least I did that for you. And so we want to find the length of the cable. See, now this is not something that 2020 Ted would ask you. I'd just ask you probably the last thing, and you'd have to think your way through. But here back then, I was like, I want to make it easier to grade, because then I could just figure out what they got wrong by asking each of these things right there. But I think it requires more understanding and knowledge to just ask you the last thing, and then you got to think of all the other stuff. So the length of the cable measured from A that is unwrapped from the wheel after it has moved 6 feet down the rails, right? So here's the 6 feet that it's moving right there. So really all we're doing is we're trying to remember that it's going to be like the amount of circumferences, if you will, of that hub that's going on right there. So If we wanted to get the circumference of something, we would take, if we want to figure out the length of it, I'll go delta S is going to be the delta theta times the radius of the thing, right? R times theta in radians equals the arc length of the thing. So we could get the delta theta by taking the distance it travels divided by R. Or we just take the 6 feet that's moved divided by the radius, and of course that has to be in feet, and so we get 12 radians. 12, that says radians, that's a rad right there. That's rad, right? So, oh wait, I said 12, yeah, but then the cable unwraps around the wheel, right? And the wheel has a radius of 2 feet. So if we want to get the length of the cable, the delta L is going to be that delta theta times, and I guess I should write this as the hub, times the R of the drum. What did I call it? The wheel, I guess. I should have called it a drum. So this is the 12 times, and this is a 2 foot right there. So it's 24 feet. Just geometry. And then the tension force is constant and acts along the distance right here. So the external work that's being applied right here is going to be, if we were putting the thing horizontal right here, here's the end of the cable, and we put that force and the tension on it, and where we're gripping it, right? We can think about if we're gripping it at a particular point and moving it to right there, this is the distance that the thing is going to move, that it's unstretched right there. So that's going to be the U1 to 2, the work is going to be the tension of the cable times the delta of the length right there. So that's going to be 16 times 24, right? Because the cable. And I might even actually, I start to ask myself, like, yeah, but the thing is also translated. Should I? I'm kind of thinking maybe I should have right here. This is the external work, but I could start to argue with myself. I'll let it go. I had a team of experts that agreed with me on this, but I could start arguing the point because the thing is going to translate and going to move. So if you unstretch the cable, you should also be the amount of distance that it moved. Interesting. I'll have to give that some more thought. No, it's fine. This is fine. This is correct. I'm just thinking it. I try to put it into terms and like, yeah, that's gonna be right. And okay, so the potential energy that's going to change right here, the PE that's going to change. So the potential energy at state 1, right? So that's just going to be this distance to this distance right there. So we really have to take. Let me see. Now my mind is all like thinking about like trying to argue this thing over. So the potential energy at state 1 is going to be, well, you could have the gravity potential energy and the spring potential energy, but the spring is unstretched. So what we're going to do here, okay, so, and it does tell me using the datum as a reference. So it already gave me that datum. So there you go. That's easy enough. That's just mg. We could call it Y1 if we want to. And the mg, it's in feet. I mean, it's in pounds, right? So the whole drum weighs, what's the drum weigh? Where does that go? 60? It's a 60-pound wheel, yeah. And 5, right? So that's silly enough. That's just 300 foot-pounds. And let's see, I now asked the potential energy at 2. So that's going to be mgy2, but plus 1/2 k, and let's say del 2 squared. So now we have, once again, 60, and after it's moved down that distance, did I do that out? Yeah, I should have done that out somewhere. At Y2. Yeah, I say it's 2 feet, but I should be able to find that somewhere, right? Maybe I did that earlier. Yeah, I should do, what I should do is I should find what this height is going to be right here, this Y2. And that should be really like 5 minus 6 times the sine of 30, right? And that should, the sine of 30, it turns out to be 0.5, right? So, I don't memorize that kind of thing. Yeah. So yeah, that comes out to be 2. Sure. But I really should have calculated that somewhere in here. Oh, no, I do. Right there, dummy. Yeah, okay. And then 1/2 the K of this thing is 12. And the amount, it's going to stretch 6 feet. That's a long spring to stretch. So that's 396 foot-pounds. And then we can figure out what the kinetic energy is going to be, because we're going to write out our main equation. Okay, there you go. We write out that the KE1 plus PE1 plus U1 to 2 is equal to KE2 plus PE2. So we could just say the kinetic energy at 1 is going to be 0, right? You should probably have written that at the very top. And then we had 300, and then this is work added to it, 384. We have kinetic energy 2, and then we're going to have the potential energy of 396. So the kinetic energy at 2 ends up being 348. And now if we want the velocity at the center of the wheel, right, we're going to have to get that kinetic energy. And again, I didn't leave myself enough room, because it's like, why would I have left myself enough room? Why wouldn't I have just planned this whole thing out and gotten to the correct slide? Where'd you go? Come on. Come on. And kinetic energy, though, at 2 is going to be 1/2 I omega squared, omega 2 squared, plus 1/2 mass of the thing times the velocity at the center squared. And I think I should have gotten what the I was going to be of this thing. It's just going to be mass times, and did I use K? What symbol did I use? Did I use anything for the radius of gyration? A lot of times that K gets confusing. I didn't use a thing. On here I did, though. Did I use... I did use that silly K. It gets confusing. I hear. So, what did I wrote? What did I write down there? Hub, KR radius of gyration. That was weird. Radius of gyration. Anyway, that K is not the spring. That's the radius of gyration. Really should call it R or something. And so that should be like 60 over 32.2 times, and I said it was radius of gyration is 8, but it's got 8 inches, so it'd be 12s. So it'd be squared And so that ends up being 0.8282, and these are slug feet squared is what the moment of inertia of the thing is going to be. And so we go 1/2 0.8282, and the first thing asks for the velocity. So we can solve these in either order that we want to, but because they asked for that one first, or I did at least, we should use a little kinematics and relate the velocity of the center to the omega, right? And so that's just going to be velocity of 2 is going to be the radius of the hub times omega 2 right here. And the radius of the hub, we remember, is going to be 6 inches, right? So it's just 0.5 omega 2. So we have 0.5. What? Let me turn it the other way. Write it the other way. So there you go. Omega 2 is going to be equal to, now just 2 times V2. There you go. Yep. 2 times V2. Because that would be the omega squared. And then plus 1/2, and then 60 divided by 32.2. And times the velocity squared, right? Yeah, velocity squared. Velocity 2 squared. So we could set that equal to, this whole thing can be set equal to our 348 that we just found up above. And so we get the velocity of 2 is going to be 11.60 feet per second. And that's moving downwards that way. They did ask for velocity, so a correct answer requires an arrow and maybe even say the degrees. Really should put that in there. And then lastly, for the last one, we want to get the omega 2 is going to be equal to 2, like right up here, just 2 times V2, 2 times 11.60. So we get, that's going to be 23.20 radians per second. And we could just assume that they meant that we want the vector. So when we get the 23.2 radians per second, we could also say that it's going to be moving down counterclockwise and make that a vector as well. So here's a working energy. Let's see, we could have done, other things we could have done in the thing. We could have put some kind of, I don't know, some kind of moment, external moment onto the thing, so that we now, we had also external work. We could have put a friction in there somehow. A little tough to put the friction in there because it's, we usually don't use the friction, at least in our kinds of problems, when we have that rotation. We could have said the friction created a moment, right? We would say something like that. Maybe there was friction maybe there was a bearing or something in there. There's friction in the bearing that caused a certain amount of moment or something along those lines. Okay, how do we know the way the arrow goes? Well, I think the easiest way to do that, if you ever have a question, is to try the instantaneous center of rotation if you possibly can, right? So ICR is really helpful. So if we're on a slope right here, and there's the hub, and here's the wheel, we know the ICR, we know the velocity is right there, it's the center, and right there is we know the point of contact without slipping is going to be the instantaneous center of rotation when it comes to a wheel. So we can confirm that it has to be going counterclockwise. Make a sense? All right, so let's see. Scrolling up there, we want an angular acceleration problem. So do you mean by that let's see, I got to move my mouse over here. I don't have any of those up there, do I? I'll go down here later. Do you mean an acceleration problem like here, or do you mean one of those ones where we're just doing where something is on a fixed point and it's spinning up and it's spinning down, or it has something tied to it like belts and that kind of thing? Antonio. Did I skip over anybody? Like the problem on page 13. On page 13 of the final review. So I don't have them numbered the way that you do. I didn't print them out because I move and change them around. Let's see. I'll go to that page and see which one you're talking about. To exam prep. Right? You probably answered my question. I could just go look and see what you just said, but I'll go down here and practice problems. And because somebody else already referred to them as a page number, so I should probably just see what you mean. Oh, come on, man. Oh, this guy. Oh, that's the one you mean. Okay. That one. Okay. Yeah. See, I was on another page and I couldn't see what the chat was right there. Okay. And by the handwriting, I can see this is my good buddy, Sean Munnis. My wife says that, anyway. I'm a real big fan. This guy I worked with at Coast Guard Academy, he was just a brilliant guy, and we got along like really well. It's really nice when you have people that you just hit it off with and you have a good working relationship. But anyway, we had a lot of mutual respect. He went on. He left the Coast Guard. He was only a lieutenant, which that sounds kind of like condescending, but I was lieutenant commander, so I can look down on lieutenants. And I was much older, but I respected the hell out of that guy. And he went to go work for Tesla. It was pretty cool. It turns out though he didn't like it. After about 2 years, he left. But he worked directly with Elon. I mean, this guy had 2 master's degrees from MIT, one in mechanical and one in naval architecture, marine engineering. Got him at the same time. He is a brilliant dude. Anyway, let me see. I just started doing the problem without talking about it. Given instance, slider block B is traveling to the right with a velocity and acceleration as shown. Ta-da. Maybe I can learn from my previous experiences and make this thing smaller, because it doesn't need to be projected up onto a screen, so you'll totally be able to see it. I just discarded a lot of that shit. But anyway, hopefully nobody will mind. Are we still recording this? Let me double check that while I get this thing down. Yeah, 53 minutes into it. And boom. Okay. So add it's going at 6 inches per second to the right and accelerating to 3 inches per second to the right. And we want to determine the angular velocity of it using the method of instantaneous center rotation. And determine the angular velocity of the wheel, omega, and then determine the angular acceleration of the wheel at this instant. Okay. So, well, it turns out that this is like one of those trick questions when it comes to this. We'll see. I'll draw it on board on here, but we can see that if we want to draw the instantaneous center of rotation, we want to go and take the line that's perpendicular to the velocity at B, and then take the line that's perpendicular at A. And it's really, really easy to fall into this trap. Is that the ICR? You can tell by the tone in my voice. It's not. That's not the ICR. That's the direction the velocity is likely to go. We would draw a line that's perpendicular to it. Ah, look what we just found. The ICR is infinite. Therefore, no rotation. This answer is 0, you tricky bastards. Well, no, this guy's 0. No, wait a minute. Yes, that one's 0. This one, however, right, if we do that, if we draw the bar over to the side, we could see that this is the velocity of B, and this is the velocity of A, and of course they have to equal each other because there's no rotation. Therefore, we could find from the wheel velocity of A is going to be equal to 6 inches per second, right? But he's got an angular velocity. I just call him A right here. So VA is equal to omega A times RA. So omega A is equal to VA over RA. And so that's going to be 6 inches per second. And let's hope that this thing is in inches. The radius, you could barely read it. Be nice if you made that a little larger. That's 5 inches. So that's going to be 1.2 radians per second. And we know that it's going to be clockwise. So if we were being good, we would write that out, 1.20. Give it 3 sig figs, please. Okay, and now we want to do the angular acceleration. So that's the acceleration problems are a little tricky, but don't be intimidated by them. We just methodically go through there. What's good practice is to try to figure out the things that we know. And something that we know easy enough is any time that we have the angular acceleration, the angular velocity, we can find the normal acceleration, right? So the normal acceleration of the wheel is going to be the down in that direction, right? It's going to be, I could have just drawn it on top of this, right? But I'll draw it on top of theirs, okay? So there's the A of, let's call it B with respect to O, or normal. It's really just the normal acceleration right here. It's going to be equal to that omega B squared times RB, right? Or writing that somewhere, we get it 7.20. And I guess I went ahead and jumped the gun. I should actually put the numbers in. 0 squared times our 5, and that ends up being 7.200 inches per second squared downwards. That'll be helpful to us. And we can kind of guess, maybe. I guess I can guess. Let me see if I guessed correct. I don't have this written out very well. I didn't print the thing out anywhere. But we have VB with respect to O, which is really just VB squared right here, is going to be not squared, but to the T. It's going to be the acceleration of B times the radius of B. That's something we don't know. Then we take the acceleration diagrams, 3-diagram method here. And we take the, whoop, don't do that. Accelerations that we know. We know the acceleration of B. We don't know this acceleration. I'm assuming it's going to the right. I got to be careful with that. But if I but I just be careful. If I get a negative, then I know I did something wrong. Actually, a lot of times I will just leave that alone. I won't commit to it. But I do know that I have the acceleration of, I called this the wrong thing here. And you guys let me do it. Let me fix all of these. This is A Where else did we go wrong here? Okay, you got A. This is A. This is A. This is A. A. Did anybody else wrong here? All right. Sorry about that. So often, they're lettered the other way. So there you go. The acceleration of A, but that's all. I should say Y, right? Which we happen to know that this is A, Y. It's equal to that right there. It's just like this one right here is A, X is equal to the tangential one right there. So we know B, so let's use that one at both places. And then let's pin it at the place that we know. And we could put in on our other accelerations onto this. We can say, I'm going to, what's the way to do it on here? Made a guess of this acceleration right here. And that's the acceleration of AB. That means that I have, and I didn't leave myself a whole lot of room. Would have been nice of me. A with respect to B in the tangential direction, right there. And yeah, okay. What is going to be that direct is going to be right here. I didn't work out what my angles were, so I got to be a little careful of that. Maybe it'd be a good place somewhere up here, somewhere along the line of taking a look and seeing what this angle is going to be. So we have, this is actually ends up being 10 inches, and the hypotenuse is 12 inches. So if we were going to take this, and maybe I'll go beta, and beta is going to be the inverse cosine, inverse sine of 10 over 20. I think we could guess that, right? Isn't that going to be 30 degrees? 10, 20, 0.5. Yeah, I know. Isn't it stupid? Yeah. 30 degrees. Duh. So, looking down at that, the way I have it is going to be right here. This is where the angle is going to be, that angle beta. That 30 degrees is going to be stuck down in there. So I can go what the X direction is going to be. The Y direction is actually going to be my better bet. To start off with the Y direction, because I know everything in the Y direction, right? I know what this guy is. So I take the, I will write out the equation, right? So we're doing it for A. The acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B, tangential, plus A with respect to B, normal. But we know because the angular velocity is 0, no rotation, right here, that goes to 0. That's a simplification. It helps us out. So we'll write out this thing in, I just said I was going to do it in the Y direction because we know everything. We know everything in the Y direction, so that's good for us as a strategy. I'll just use numbers. 7.200, and let's make it negative because let's go up and down, positive right here. All right, so that's going to be equal to, and B is completely horizontal, so that's going to be 0. That's so nice of us. And then we'll also take a look at the acceleration of A with respect to B in the tangential direction, but only in the vertical part of it, right? So we know that that's going to be A with respect to B tangential is going to be equal to alpha AB times LAB, which was 20 right here, right? And the Y direction component is negative, right? So we take our alpha AB times our 20, but it's only going to be the cosine of our 30 degrees. And did I do that right? Yeah, negative. Okay. And so that ends up being alpha AB. I didn't, the way he wrote it out was going to be different. 7.2 divided by 20 divided by the cosine of 30. I get, boom. Yeah, okay, so we never wrote it out. I believe this is going to be right, unless I did some stupid math thing wrong. Radians per second squared. And it's negative. Yeah, so I picked it correctly as counterclockwise. And then in the x direction, we don't know which direction it is. So I'm just going to assume that it's going to be positive, right? Just to make it, you could just draw it in there if you wanted to, but just make it positive. So that's AB is positive, and that's going to be our 3 inches per second squared. And in terms of our tangential one right here, we see that too, as drawn, is going to be the negative direction, right? That component would be, I'll just do it in yellow, like that way right there, be like that, opposite from there. So that's going to be negative. That alpha we just got 4.798 times the length 20, but now times the sine of 30 degrees. And so what we're left with is, let's see, times 20 times 30 times the sine of 30 times, that was stupid. Yeah, it was 10. And then it's going to be minus 3. Okay, so I end up with a negative. Is that true? I'm a little concerned by that right there. I'm getting a different answer. You know what? I might have gotten, is there any chance he was wrong on this? I think I messed something up here. Yep. So that's what you get for not reading. Just read the thing. But he did it just a little slightly different than I would have done it. So that was the 7.2 divided by 20 divided by 30 cosine 30. Yeah. Don't know what I did wrong. 4157. Right? So 0.4157 times 20 times the sine of 30, right? And then I subtract out. So, okay, so I get a negative 1.157. This is inches per second squared. And then if I had left myself a little more room, I could go back up onto here, and I could see this is actually going to be in this direction right there, right? And so then I would find that alpha of my, I guess I'd call it alpha A, is going to be equal to my acceleration of A in the x direction, which is actually the tangential direction, divided by r of A. Yep, I'll explain that here. And so we get 1.157 divided by 5, and we should get our 0.2314 radians per second squared. And so now right up here is the full answer, right? And we could see that it was actually counterclockwise. Gosh darn, poison ivy. All right, so when looking at looking for the ICR, I'm trying to find some blank space. Okay, yep. we know this direction, right? We have this VB right here. So we can draw a line perpendicular to it if we can get the stupid pen to work. Here's the line that goes perpendicular to that velocity. But we also know that if the wheel is spinning and we're at that top point right here, that it has to go along this line, right? I mean, it depends whether it's the wheel is spinning to the left or spinning to the right. Depends on which way if it's going to go left or right. But we know it has to be horizontal, so it has to be this way. So its line that would pass through the ICR has to be right there. And because they go together, right? Because they never touch each other, that means the ICR has to be infinite. And the only way that could possibly happen is if the thing is in pure translation. And therefore, there's no omega. It has to be 0. Omega has to be 0. Does that make sense, Nick? No problem. Okay, so I got a request for the last problem, which I don't know what order they're in on the thing that you have. A mass moment of inertia problem, is that right? Okay. Is that even in my packet? It is not in my packet. Well, I'll have to just figure it out then. All right, where'd you go, mouse? Oh, you're over on the other thing. We'll keep it for now in case somebody asks something later. Go back on it. Computer is slowing down. And so is the professor. As my good friend Alicia wrote out the solution to this one. She liked to have these tables of stuff. All right, so at least we know we're going to be able to know what the answer is going to be. Let me copy this and bring them back up to here. I didn't mean to do that. I got to right click and can I just paste it? Sure, okay. Yeah, that might be enough space. All right, so we want the location of the center of the mass. And it really is a lot easier to use a table for most things that have, like, if it has 3 parts or more, I use a table. But a lot of times that might be just unnecessary if you just had 2 parts. But if somebody asks you for a table, then you make a table. So if we wanted to get the mass of the piece, like, is this one of these guys? Oh yeah, it's got a total mass of 2. These are such a pain in the ass. I always hated this thing. So I actually have to think out loud. When you do that, I'd rather create like a density for myself and think of it in those terms. It's just not the way that my mind works. To figure out, like, so if you know what the like, you can get an area density if you wanted to, and so sometimes that's the way that I would approach this. I would say that the total area of this thing was going to be equal to, or we could just take it as a partial ratio. Anyway, I would say that we go pi over 4 200 squared minus 75 squared, right? Like, I never ask for questions this way because I just don't like them. But there's like I don't remember off the top of my head what the method that's it's convenient is to go through this without having to actually do this part of it here. But this is it's a necessity thing. All right, so the area of this is 27,000. Almost be better to do it in meters, but I go 27,000 millimeters squared. And so I'm going to create this density for myself. That's going to be that mass divided by the area. This is like an area density. You could assume that it's like 1 millimeter thick, right, and then make it a real density. But then I would say that's going to be that divided by, or the inverse of that right there. So 7.408 of the thing. And you know, now that I'm thinking about it, if you consider it to be uniform density, we can just find the centroid of the thing, and that's going to be the same thing as the center of mass. So what I just did was kind of unnecessary, but that's okay. And so, but no, it would be kind of useful. So I could find you know, we know it's going to be along this line right here, the center of mass. And it's probably going to be biased to be down here, because that's where we're removing space from up here. That's going to shift the center of mass down. So we could take the sum of the masses times the individual y distances divided by the total sum of the masses. But since the density is going to be equal to each other, that would be like the same thing is the sum of and the thickness is the same. The sum of the areas. And so the area, so what we do is we would take the area of the top, so you know, you notice that those go away, and take the area of the individual ones. So we go pi over 4 times our 200 squared, but that's going to be times 0, right? Because we're going to use O as the reference point, right? So we can measure everything from O, so that doesn't do anything. So we go minus pi over 4 times 75 squared, and its distance is going to be 100. And then divided by, that's just going to be the total area, what I just calculated over there, right? The pi over 4, 200 squared minus 75 squared. If we do that, we get 75 squared 100 times pi times 4 divided right here. And so what I think I'm going to do, and then I get 27,000 here, 27,000. And so I get a negative 1.636 millimeters. Is that right? No, I get 16.36. Is that what she said? Yeah, it's negative 16 right here. So that's where we get that center. And then for the mass moment of inertia, that's a lot easier a lot of times in a table. I could have done that in a table as well. So I ask for, we can call this part 1 and this part 2. All right. So we take the I of, and we wanted about the axis. We want about the axis, right? Okay, so we want about the O. So that actually helps us out. So I of O is going to be I 1 minus I2, but plus M2 times the distance it has to move right here. So from this distance to right here, so I'll go this like I don't know. We could call it something like I don't know. Just call it D for right now. It's the easiest thing to remember. So both of these are going to be disks. So it's going to be 1/2 mr squared right there. So right. So we find and the mass of this thing. Like I said up above, I wanted to do a density of the piece. So I could say that the mass of 1 was going to be equal to the area of 1, right? So the area of 1 is going to be pi over 4 200 squared times my density of 7.408 e minus 5, right? Which is going to be 200 squared pi times 4 divided right there, yeah, times, so that's going to be 2.327 kilograms, and therefore we know that M2 is, of course, is negative 0.327 kilograms. And so I go 1/2 2.327 0.2 squared minus 1/2 0.327. It'd be nice to have another sig fig right in there, but that's not. Actually, I could do it right here. Boom. 373. Anytime you can eliminate some source of error, it's a good idea. And I guess I decided to do it in millimeters. I didn't tell you what the units it were, but most of the time you want kilogram meters. You don't want millimeter. Kilogram meter squared, not kilogram. Kilogram meter squared, not kilogram millimeter squared. Mushmouth. 0.1 not 0.1 squared, 0.75. 0.075, dummy. 0.075 squared plus, non-negative room now, 0.3273 times the distance, which is 0.1 squared. And so it wouldn't kill us to get in between numbers here. So you got 0.2 squared times 2 divided 4.655 e to the minus 2 is what that is. This part right here. .075 squared times 2 divided, and I get 9.205 e minus 4, and I'm going to add that to 0.1 squared 0.3273 multiplied by it, and that should be 0. No, I could just do that in my head, dummy. 3.273 e to the minus 3. So you add those two together, but you subtract it from there, and we get an I about O of 4.235 e to the minus 2 kilogram meter squared. Tell me I got it right. There you go. And let's see, what did she do as a thingy? Oh yeah, she did. Oh, she likes to. She always enjoyed that. Yeah, that's her modus operandi, is to keep things like those, like fractions. I think it's a University of Rhode Island thing. She went to University of Rhode Island, got her PhD there, so in ocean engineering. I miss Alicia. She's a good coworker. Any more questions, requests? How are we doing on time? Is it? We've been here for about an hour and a half. We can keep it for now. I don't know. I shouldn't do that. An hour 24 minutes worth of recording. And look at that look at the little wheel of death. What is going on with you? Oh. Okay, it's trying to save it. That's why. So I should have this loaded up on my phone all the time right here while I'm not doing this online teaching right here, right? So I should just play like a little Pink Floyd. Is there anybody out there? That's a good song. Is there anybody out there? Huh? Is there anybody out there? Let's see. It's a Pink Floyd song, Off the Wall. Anybody familiar with The Wall? It's a great album. You can hear me, right? Hello, is there anybody in there? Just nod if you can hear me. Is there anyone at home? So I'm singing Comfortably Numb now. Okay, give me a request. Requests. Stop singing. That's a good request, right? I'll start playing guitar if you don't watch out. Projectile motion, something. Okay. Oh, ready. So sometimes I can confuse myself on a projectile motion problem. Let's see. I'll pick one of the guys from. I can't keep losing my mouse, man. Oh, did I close down Edge? I did, didn't I? I'll cheat. I'll pick one of these guys. No, you dummy. Just close it down. I can't open. I have my key. I don't have my keyboard accessible to me right now at this moment. And when I try to use this little guy down here, it gets all fudgy up on me. But I was going to pick one over in this side. E D. Come on, right in there. E D. You bastard. Come on. E. I'm pressing down, you bastard. E. You such a jerk. All right, so projectile motion where the path is known, projectile motion where the thing is known. See, it does that. The son of a gun. I just wish things would go the way that I want them to go all the time. Why can't I just get my way all the time? There you go, Edge. Microsoft Edge. There you go. I don't like Microsoft Edge, but there you go. All right. So we have the projectile motion problems here. You could go. So let's see. We'll open in a new tab. Open in a new tab. Here, just picking random ones here. See stuff you could choose from. The path is known. Ooh, parametric. I wonder what the hell they mean by that. Let's see what they mean. All right. So let's see what they mean by this parametric one. Nah, you don't want to do that. I mean, we could, but all that is just taking the derivative of the equation that the thing moves. I don't know if you really call that a projectile motion problem. I don't know why he's calling it that. Right here. See, does he mean the same thing over here when he does that? Yeah. I mean, it's true. It's definitely something that, if you had two different, if you have two different equations right here. It says sure, you can plug them in, and you could take the time derivative of them, and then you could find what those are. But here's another one where that's what he means by the path. Okay, yeah, that's another one where he means by the path. It's not really projectile motion. There's projectile motion, although, yeah, you got something like this right here. Okay, so we got this bird carrying a juniper berry. Suddenly releases the juniper berry. So the bird is coming up at 10 meters per second. So the berry is coming up and it's going to land. And so you want to predict where it's going to land. And if you had the G wrong, right? So this guy, he takes off 3 points if you get the acceleration of gravity wrong out of 25. I don't know. Seems that's a little on the mean side. We got this kicker right here. Alternate approach, clever. So let me work my way through this right here. So I will come back over to here, and let's pick him out and do him, because there was two approaches. So instead of me reading to you the approach, let's see, I will walk through it. Some learning to be had there. Just get the stupid computer to do something I want it to do. Come back over here. Let's see what the little picture looks like, because the picture helps. I have a really crazy projectile motion problem that was just evil that I did in my book. It's evil. All right, so in most of the time, the thing that we care about the most in projectile motion is that we have two things going on at once. We have something going horizontal and we have something going vertical. So in the horizontal direction, it's x is going to be equal to the original x plus the velocity, original velocity in the x direction times time. But we also have the y position is going to have this equation here. Original velocity in the y direction times time minus 1/2 gt squared. And so what we could do, the videotape of a football player kicking the long field goal, it is observed that the ball traveled 185 feet to the goalpost right here. And he's going to protect you. We're going to pretend like he's kicking it off the ground, I think. The ball was in the air 2.8 seconds. Find the initial velocity of the ball and the angle at which it was kicked. Okay? So what we do here is we could just find what the time is going to be, right? We could just figure out what the velocity in the x direction is going to be, because we know time and we know the distance that it moved, right? So it's like 185 equal to 0 plus VOX times that time, which was 2.8 seconds. So what we're left with is the VOX was going to be, one second, let me think, it's going to be 185 divided by 2.8, which isn't hard to do, right? So he gets 66.07 feet per second. Yeah, sure. And then in the y direction, what we could do the same thing. Do we know the field goal? Oh, wait. Oh, to where it hits the ground. Boom, 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 boom. Okay. Duh. So all we needed to do was to find well, y is O and y0 are going to be equal to each other, right? Plus VOY times t minus 1/2 32.2 times t squared right here. And then so VOY, and I wasn't looking at the solution just now as I was doing this. I was riffing, but then I just took a peek just now, and I actually was doing, I think, the alternate way. But anyway, you notice that time cancels out, or one of the times cancels out. And so what we're left with is it's going to be 1/2 32.2 divided by 2 times our 2.8. Is that going to give me the same thing? I better. 2.8, 2 divided 32.2 times. I get 45.8.08 feet per second. And then, so we're going to, VO is going to be the square root of 66.07 squared plus 45.08 squared, and get 79.999999999 probably, because it probably turned out to be 880. And then the theta of that is going to be the y over the x, right? No, it's going to be rise over run. That doesn't make sense. It's going to be, why is it, he makes it seem, no, okay, yeah. Rise over run, inverse tangent. Right, it suddenly, I was just thinking of them backwards. Rise is this, is the y, the decimal place, 66.07. 45.08, 66.07 divided inverse tangent, 34.31 degrees. So, and that's what he was asking for right there. So there you go, boom and boom. The other way that he did it, he did the same way as me. All right, so there's the clever one. The clever way is, he found that 66. Yeah, no, it's the same way. No, I don't know why he said, yeah, I'll bring it back over. I'll show you what I mean. Will not let me bring that over? Why wouldn't it do that? You can keep it, I don't care. Oh, I guess. Oh, I see, okay. I'm so confused. The mouse doesn't like it when you try to drag something from one screen to another. But he was saying, these look the same to me. Why did he say clever next to this one? I mean, this is what we just did below, right? So really should do one that's more challenging, but you can make them too challenging. They can, projectile motion can get kind of nasty. Sometimes you have to use, I'm going to say this the right way, you have to use like a half angle identity. It's when you have to find the angle. Sometimes that could be kind of annoying. I'll try to see if I can find this myself. Let's see if I can bring him over here. I've never asked this question. I'm not going to ask this question. It's just kind of a dirtbag move to do. Oh, I know I could show. Yeah. Just go to this guy and go to the Engineering Dynamics course companion and go to, I could open the manuscript will take a time to load up. We could go to draft and go to, will it be class 1? Oh, I don't know now. No, of course not. Class 3. And kinematics of particles. Dragging, not letting me. There you go. See? And here's my projectile motion problems. Here's my new version of Newt Dog. I drew him make it look a little slicker. Although I don't really like the way that looks. I think they were able to make it look better in the print right here. But I go and you could find that there's actually two different angles or two different, here you have two different velocities to be able to land it into the thing, so if you found one is 45 degrees and one's 30 degrees, that you could land something in the same spot, right? And here, so the strategy is that we replace the time. We solve this equation in the x direction for time and place it inside the y direction right here. So we replace the time everywhere with this, and then we end up with an equation that looks like this, which is always interesting to me, that the VOs cancel out right here. So and they get the sine divided by the cosine, so that you just have the tangent like right in there. But then you can solve for VO as part of that, and you don't have to use a quadratic equation, and you can just get this equation and then just plug stuff into it. Looks to me like I might have left something out right there. It looks, no, I guess it's just a couple spaces or something. Anyway, that you can, so now you have, this is really just the equation of using the geometry of the thing. And so when you have a different angle that you're putting the thing in there. Yeah, there's something that needs to go inside there. There's missing something right there. Damn, it's always something. But I had, and there's me just plotting the thing out. I had like an evil problem. Okay, well, we talk about relative motion. Here's the evil problem. We have the relative motion, and yeah, so we got these two boys, and they're brothers. I think they're brothers. Yeah, they're brothers, right? And they're shooting basketballs, and they shoot with the same velocity right here, and it lands. And we want to know that what makes it evil is it's a multi-step problem. But we want to know what the position of one of them is going to be when the other one lands, right? So what is the relative velocity of B to ball A when the ball hits the hoop? And again, this would be like just the meanest of problems to like assign for an exam, because it really would mess with your head for a little while. But you get a lot of the same things going on, right? A lot of the same ideas where you just replace those equations, right? You just stick one of those equations aside the other equation. But now, if you want to solve for theta right here, right? If you want the angle to theta, you need to remember this one identity that isn't necessarily something that you would remember. Because you have cosine squared on the bottom, cosine of theta squared on the bottom, but then you have tangent of theta up here. So the way that you want to do is recognize that 1 over cosine squared is equal to secant squared, and that secant squared is equal to 1 plus tangent squared, right? And so what you could do is you could put 1 plus tangent squared here. Now, if you notice, we have a tangent of theta and a tangent squared of theta. So we can use the quadratic equation to find, and I just set it equal to z, right? I just said that the tangent of theta is equal to z, just so it didn't look quite as ugly. And so we have this thing right here is the quadratic equation. And now we can solve for z, and we get two different answers, right? And so these are the two different angles that the brothers can shoot the ball at and get and for it to make the basket, right? And it didn't matter what the the initial velocity was something that we did know the initial velocity. Initial velocity was given. So at that velocity, there's two separate angles that we could shoot it at. So what you do is you could find the time when one of them is going to reach the basket, and you know the one that's actually with the smaller angle is going to reach the basket first. The other is like shooting out a big rainbow, right? So one's more like, you're throwing you're throwing more closely directly towards the basket, and the other is you're throwing up this big arc, right? And they both are going to reach the basket with that same initial velocity, but the one that with the smaller angle is going to reach it first. So you could find what that time is going to be based on the x displacement in that using the cosine right there. And then you could figure out what the velocity components are going to be at that time, right? For one thing, the x component is always the same, but now we need the vertical component of that at that time. Yes, at that time, right? So we figured out that time. At the same time, what you could do is you could figure out the components of the ball B at that same time. And now you could turn them into vectors, right? You could have the vector of A, you know what that thing looks like, and you have the vector of B, you know what that looks like, because we have the components of them. And now we can get the relative velocity between the two, and we can get what the angle is. So here's what that means. Here's what they were asking, it was me, I invented this problem. Because I was trying to combine something that would make, I was trying to write a book that has a lot harder examples into it. Because students complain all the time that the examples are easier than the homework, right? And then quite often they'll also complain that the exam was harder than the homework, which I tried my very best to make sure that's never true. But it could be true. I've had lots and lots and lots of professors who made the exams much harder than the homework. I've had lots of professors that never finished an example in class and never really never graded our homework and then gave us an exam. And you can now be playing the world's smallest violin if you'd like to. It's totally up to you of what kind of instrument you'd like to play. So we're working down. We're close to 2 hours here. Any more? What do you got? You guys got more? How's your endurance going right here? My hand hurts like hell. Poison ivy. Why did poison ivy happen? How did it occur? Okay, now whether you're depending on your belief system, right? You could believe in evolution, or you could believe creationism. Either way, how does poison ivy exist? What evolutionary principle caused poison ivy to happen? Or if there's a guiding, all-knowing entity, why would they create poison ivy? Is what I want to know. It protects itself. It adapts. The poison ivy adapted, but I'm just wondering, okay, well, it has this minor adaptation, and then time goes by, and then I guess people didn't rip it out of the ground. People didn't eat it. I don't know. It just seems to me that it's just a bad joke. It's just nature playing a bad joke on us. Maybe it's the same reason why I have coronavirus, right? I don't know. No, that doesn't make any sense at all. So topical. This has nothing to do with dynamics. But you get me talking for too long. Extra credit on the final. I love that idea. Are you asking if the finding out why poison ivy is bad as extra credit on the final? There's no definitive answer. I think the only way that I think is if it amused me, right? That would be but I think I'd rather put extra credit on the final where we actually deal with dynamics in some way. Yeah. I try to be fair, as fair as I can. So, anybody got any requests? We could probably do another problem if you want to. The tangles they form also serve as shelter, and incidentally, most animals are not affected by their irritants. Okay, so here's what scares me, is that my daughter insists she is not allergic to poison ivy and has said that she has demonstrated this by rubbing it on herself. And I just, yeah, I'm just saying, you know, there could be different breeds of poison ivy. You just don't necessarily know. But I was planting wildflowers. And maybe that's the poison ivy. That's why it was angry at me, because I was trying to plant wildflowers. Why would you plant wildflowers? Wildflowers, by definition, should be wild. But I was planting them by the side of our driveway because I thought that it would look pretty. So I raked a bunch of the leaves around, and there was a bunch of roots right there of vines. I'm like, shit, I got to get rid of those vines. Didn't think twice of it, and started ripping these vines out of the ground. Guess what? They were poison ivy. Underneath the leaves. I know my driveway well. I didn't know there was ever poison ivy there. Just leaves. But apparently, it was waiting. Yeah, I agree. Yeah. Now that I have poison ivy, I remember that. I usually do. This time I wasn't. I was out of practice. You know whose fault it was? It was my neighbor. I have a new neighbor. The neighbor right here, I have a long driveway, and this is the neighbor that's butts right up against the driveway. His name's Joe. Joe came over and distracted me. Joe just kept talking. And Joe is one of those guys that knows everything. I mean, Joe has been everywhere and done everything. He's been a conductor in a big band. He's led, he's been in charge of like 3,000 people at NASA. He's currently working an electric boat. Joe teaches ballroom dancing. Yeah. Always blame it on the neighbor. I could do a rigid body, Newton's second law problem. Yes, I can. I hear what you're saying, Sydney. This is not time to talk a bitch about Joe. I got it. When you get a chance, sure, I got it. You know, no problem. I'm always getting yelled at. That's all right. I don't mind. Okay. Well, let's go back to Fowler. What's the name? Bedford and Fowler. That's just got a great name. Bedford and Fowler. And take a look. Could actually, let's see. We got to figure out what chapter that's in. It's probably in the one before this, I'm guessing. Oh, I can't read what you're writing right now. So, use Technu for poison ivy. It helps. What is Technu? Is it something that kills the weeds or solves my hand inflammation? I have blisters in between my fingers. I know, that's gross, right? You didn't want to hear that. You could have been eating something. You could be throwing up right now. Yeah, I mean, big blisters. I mean, I can't get my fingers to go back together. Helps wash the oils off your skin. I don't know if it's too late now. They're probably like wickedly in there all over the place. I look like a calamine, what's the name of that kind of horse that has patches all over it? That's what it looked like. Two-dimensional dynamics of rigid bodies, momentum principles, derivation applications, energy methods, planar. Okay, so I think it's going to be this chapter 7 in here. By the way, something I keep always meaning to include this. So to have discussion of what the equations of motion. This is a great phrase, but if you take vibration classes, you'll learn about the equations of motion. But there's an interesting thing, especially as it relates to differential equations. The equations of motion. It sounds really important. So we're going to see like page 360 something or other. The equations of motion. Sounds so important. All right, here they like to do this stuff with the cross product stuff. I don't like doing it all that much. Not a big fan of the cross product stuff. That's right. Chapter summary. Here's a problem. Oh, and that's the stuff that we just did. That's planar kinematics. How did I mess this up that much? Thinking about it. Oh, it's 360 something. That's why. Yeah. Some of these might be too hard to do. let's see, 746. Like a couple of these, some of these will be a little too hard to do. See, I shouldn't do this live because all this kind of stuff can drive you a little nuts. Trying to pick out good problems. There's always like something about the problem that goes, well, that's not very good. So like, here's one right here, the instant of release, the angular acceleration, and the normal force exerted. So this is a classic problem. Like if I was other professors, I might ask this problem, but there's other things right here. Okay, suppose the ladder here has a counterclockwise angular velocity of 1. So let me see if I could find that one in, I think he's going to be chapter 17. I was on the wrong spot. No, I want chapter 18. When you know it. Bedford and Fowler, you just got on my poison ivy list. Oh, look at that. Okay. Get a faster modem. Get children that don't steal your bandwidth. I have very nice kids, actually, but I don't want to pretend like they're bad or anything. They're nice guys. And what did I say? With this guy, he was like in the 33 range. So you could just pause these really quick and find all the answers to all these. There you go. All right. I mostly just want to know if I get the right answer or not. And I'm doing this for your own benefit because I don't want to, I don't want to ask a question that you already have the solutions to. That's right. So, rigid by Newton's second law. And I like this one's good because it's generalized, right? It isn't about a fixed point. The fixed point ones can be just a little too easy. That one's a little trickier. Maybe make it a little harder. I don't want to make it too hard. It looks, it's hard to judge sometimes by what it looks like in the solution manual of how difficult the thing is. But it did give a nice size to it there. All right, so we have this 18-kilogram ladder is released from rest in the position shown. Model it as a cylinder bar and neglect friction and determine its angular acceleration at the instant that it gets released. So the real important thing when we're doing any of these is to draw, you guessed it, the free body diagram and the inertial body diagram. It's so important. And when you go to do other classes, what I have had feedback from other professors, and they said, I just wanted to let you know, this came, they weren't sucking up to me. There's no reason for them to. Why would they? I'm a junior faculty. And they said, I just want to let you know that I have your students in my blank class, and they really know their free body diagram. And I'm like, awesome, man. That's great. I'm glad to hear it. So what we have here is we figure out what the reactions are, and reactions are going to be perpendicular right there, right? So we had to try to do our best to draw these reactions. And we're going to have a weight acting down right there, mg. But then over on the other side here, we're going to have acceleration probably going in that direction. acceleration probably go in this direction. And I think it seems to me that this guy is going to accelerate more than that guy. So we should probably have that. So I alpha m acceleration x m acceleration y. So we use our, and we also, as part of this right here, we're going to find out pretty soon that we're going to want to relate what those accelerations are to each other. All right. So, but we'll start off with where we were to begin with, and say the sum of the moments about some point. Now, it could be often the best thing to do when you don't have a fixed point is take it about the center of gravity. And when you do that, then you do have one of those special cases here where you have the IG alpha. Right? So the G is right here in the center. And maybe it would behoove me, which is a great word. Ooh, it'd be great if I could undo that, but I got to draw it again now. That was a terrible drawing. I could write G. It would behoove me to keep track of what these things are right here. All right. So, and I can actually find what that IG is going to be. Maybe I'll get that out of the way. It's going to be 1/12 mass times length squared. So 1/12, 18. Length is 4 squared. They didn't bother solving it for me, by the way. I think it's 1.3333. It seems like that's familiar. We already have this. 18, 16 times 12 divided. And I got 24 now. What is wrong with you? It's 18 kilograms. It's 4 meters long. 4 is 16. No kidding. 18 times 12 divided. 24. Wow. See? Never get it right the first time. Well, how about that? So if we take the moments that are happening here, I think it's actually going to be easier. It's usually easier for me instead of to break things apart anytime I can. And so I am going to have that angle and that guy right there. So I'll go FBY and FBX, right? And then I might also want to know just some references right here, because this is 20 degrees. So I'm thinking that's 20 degrees. And that right there is 30 degrees. So my FBX is going to be equal to FB times the sine of 20 degrees, and my FBY is going to be FB times the cosine of 20 degrees. And then the distances that I'm dealing with right here, of course, it's going to be to the center of the thing, so that just makes my life even better, doesn't it? And so this is going to be like 60 degrees right here. So as I'm coming through this, and we're going to the center of there, this distance right here is going to be 4 times the cosine of 30 degrees. .4 something or other, 64. But divided by 2, dummy. I should have just took a 2. 2. .732. And let's see, so the distance right here is going to be 2 times the cosine of 60, which should be 0.5, right? Dummy, 1. And this distance right here should be times the sine, 2 times the sine of 60, which is going to be the same thing, right? 1.732. Damn it. I'm still plugging it in. 1.732 meters. All right. Got ugly geometry out of the way. So as we're taking a look at the moment over here, we're going to take FA. So we're going to just go FA. And we'll make sure we get the correct directions. Plus, so FA is going to be negative times our 1.732. And then we're going to take FBX. So that's going to be, and that's positive because it's going counterclockwise. So it's FB times the sine of 20. And then also going counterclockwise is FBY. FB up. Forgot the moment. Do that all the time. Do that all the time. FB sine, the x direction is going to be 1.732. It's got to be a moment. And then the same thing for here. We got FB times the cosine of 20 degrees. And that's going to be times 1. And that's going to be equal to I of 24 times alpha. Right? And then we go... well, we also have 2 other equations that we could deal with. We could have the sum of the forces in the x direction, it's mass times acceleration in the x direction. So it's going to be that direction. So we're going to have that FA plus FB times the sine of 20 is going to be equal to the mass, which is 18, times the acceleration in the x direction. And then we'll have some of the forces in the... Well, I already used that color, damn it. Go purple. Some of the forces in the y direction equals mass times acceleration in the y direction. And that's going to be only FB cosine of 20 degrees. And on the right hand side, we got negative. Oh yeah, cool. Minus mass times gravity. Which we were throwing numbers in here, so we'll do it anyway. 18 times 9.81. And that's going to be equal to negative 18 times A. I should have put this AGY. I should have labeled him correctly. AGX. Okay. So far we have 3 equations. We have, we don't know FB, FA, we don't know FB, we don't know alpha. We don't know FA or FB, and now we don't know AGX. We don't know and now we don't know here, right? So we have 1, 2, 3, 4, 5. 5 unknowns. So what we have to do is try to figure out how these things are related to each other. And the best way is now through kinematics. And I prefer to use the three diagram method for kinematics. And this could get a little ugly. Not going to lie to you. But what we could do here is, like we could start out, we start anywhere we want onto this, but we have three different accelerations or things that we can try to figure out their relationship to each other. One thing that we do know is, and one assumption we can make is that the ladder does not come off of the wall, and it does not come off of this. So we do know the directions that these things, or the constraints of where these things have to go, and because of the nature of it falling, we kind of know for sure that it's going to be going down that way, and it's going to be coming down this way, right? So we have the sense of the acceleration of A, and we have the sense of the acceleration of B. Well, I have the direction too. It's not a very good place to put it. Right, and we also have the, we can break that into components right there and separate the thing out. And it's probably easiest to use A as the reference because it's only in one direction. So we could pin it right here, and we already are assuming alpha is coming that way. So we have that direction right here. And we can now we could get what this angle is going to be. I want to check, but I think it's going to be that same angle. That angle right there. Got to be really careful with those. But I'm almost certain that it's going to be that angle. So that's going to be the acceleration of B with respect to A in the tangential direction. And it's nice of them not to make it, it's going to start from rest, so we don't have anything in this direction, right? There is no normal acceleration of B with respect to A. So from this, we can, I think we can establish, we can establish what a relationship is going to be between these points, between between these positions right here. The thing is that we're adding in additional unknowns. But more importantly, when we get a relationship onto this, we're able to establish narrow down what the acceleration of G is going to be. That's going to be the important thing that we're going to want to find. The acceleration of G in the x direction. And I'm not going to be able to finish this problem, by the way. There's going to be a little bit of math, and it's going to take. I usually have to pore over when any amount of math in here. I have to sit around and think about it like for a good hour and change. Argue with myself back and forth. But we're going to see that we're going to have a acceleration of G with respect to A. And that's the one that we're going to be able to use and replace in with this right here and this right here. Replace those guys because we'll be able to break this down based there, and then have also have that alpha right there. So that's gonna allow us to make this connection between alpha and G. And it's really going to be it's really this horizontal direction that's going to help us out the most, I believe. But anyway, that's like the process for going through there in a generic problem. This is too hard. This is too long to put on an exam, but and even in the posted, even in the solution that they give, they use a different method than I am. But they really should be doing. He doesn't use the IBD type of thing, but I really think they should. But they use. You can see here's the three equations from the equations of motion right here, right? And then up above we have these relationships right there. To establish. So there's the 5 equations that you have to deal with, and they just punt and say it's 5 equations and 5 unknowns. Personally, I like to show the math all the way through, but I'll write it up and I'll record the solution, or I'll write up a solution to it all the way through. I know that's not satisfying because we didn't end up with a number. How many people I lose? Look at that. I still got 10 people left. Damn. You guys are playing with your dogs, aren't you? But most of the time, I tend to ask a question that's pinned. No, that's not a Newton's second law. Here's a pinned one, right? Where I have this, and the solution is posted to it. Here's one that isn't pinned, where it does have translation and rotation, and as part of it. So, I can't remember the name of he was one of the rotating faculty. I don't remember it, but it was his first year, and he picked out this problem. And the students really struggle with it, but the same ideas apply. You write the FBD and the IBD, and you do the stuff in the X direction, and you do the stuff about the center of gravity right here. And you know that the friction force right in there is going to be related, and you don't want the friction force, so you're able to use this one in the X direction to avoid finding it, and you get these things related, and you also have the kinematics. So it's the same ideas, but you methodically pick through the thing and you try to find yourself a path to being able to find a solution. It's the same idea, but this one is, quite a bit easier than that ladder problem. But that ladder problem is a classic problem. I have seen instructors ask that in other schools and other places. That's a long problem to ask on an exam. I always time the exams, and I try to make it so that I can do it myself in half the time that it would be allotted for you. That just seems kind of evil to ask a problem that you can't do yourself. Yeah, there's another Newton's second law problem. I wonder how many are on this dude's page. Let's see. Can find him. Bring him back over. He's going to come back over. You coming back over? No, you're not, are you? There you go. I don't know. A lot of people don't get a lot of courses they don't get to here. Let's see. He got particle work and energy. Those are work and energy ones. Equations of motion, particles, and rigid bodies. So you got rigid body. So you got general plane motion right here. Spool with a cable. Wheels falling with weights. Slender bars falling. So let's see. See what he did. And this, a lot of times they'll make this thing look like wicked easy, but you could see that we have some of the things happening. It's nice that it only has one force on here, right? Only, instead of having those two angled forces. I picked a doozy. But you have the sum of the forces in the x direction. You ended up seeing there's no forces in the x direction, so there's no acceleration in the x direction. That was good. So you could just take the sum of the forces in the y direction, and you could get the one of the equations that you need right here. And then you take the moments and you take it about the normal, and that's nice. Or here we're taking this about the center of gravity. That helps by taking about the center of gravity. And then you relate the center of gravity with that point at A, and you're able to find extra equations and be able to solve what the accelerations are. So you know the acceleration at A, what it's going to be. Is that what they ask? Find the accelerations of point A and the center of mass G. And here's another bar one right here. He didn't ask any. He shows you these others, but he didn't do it. The slender ball are falling. Yeah, this is more of a pinned. No, I guess it's kind of a pinned problem. Look at that. He uses a matrix to solve the thing. Wonderful matrices. Yay for matrices. But if you have more than one equation, it's good to use a matrix. We don't really do that as much in here. We got basic problems. What a basic problem right here. And that's the same as if no... What does that mean? If no acceleration at a point. If you know the acceleration at a point, great. But must find the accelerations at G. G terms and F equals ma equations cannot put in terms of equations. Okay. All right, I am tired, and I think I put my my time in, 2 hours and something. There you go. 2 hours and 20 minutes, man. I am D-O-N done. No, D-U-N done.